Hello class. Okay, so in this video we will continue with our discussion on um, graphics in R. All right. Now, so I'll start first with my dates as I have usually been doing, and then our topic is still on graphics in R. Okay. Now, but under graphics in R, remember last week we did talk about graphics for qualitative data. So this week we move on to the second part of it, which is when we have quantitative data. Quantitative data. Okay. So under this topic, in quantitative data, I'm going to discuss some plots that we can use to display quantitative data. And these plots will be, first of all, we will talk about histogram. We will talk about stem and leaf, and then also bar charts. And then lastly, we will deal with line plots or scatter plots for when we have two-dimensional data. So mainly four things. Okay. Now, so what is a quantitative data? These are numeric data, you see, and because and under the scale of measurement, we are dealing with what? Whether it's the interval or ratio scale. Okay, so these are the types of data we're going to talk about. Now, in the previous video, somebody was asking, what if you have your own data? Okay, so I'm going to use inbuilt data in now for this, but it doesn't mean that when you have a data set, that your own data set, you cannot analyze it. That is the more reason why I taught you how to read data. For example, we did talk about how we can, or I did show you how you can read data from a text file, from Excel sheets, and so forth. So you make use of that when you have your own data, or let's say you collect data from elsewhere and you want to, so you want to analyze it, then you can read it into R, and now it becomes like our inbuilt data that we're going to use for this, and then the previous one we did. So that's it. Okay, so let's first start with histograms. So what are histograms? Oh, well, for a histogram, it's just like a bar chart, but this one, because we are not having like categorical data set, these bars that we'll use will be what? Together. In other words, there wouldn't be spaces between them. So that's the only difference between this and a bar chart. So how do we construct histograms in R? In R, to construct a histogram, we use the command hist. Okay, so we use hist to do this. Right. Okay. So let's look at the help files for hist. Okay. Now, so histogram is in the graphics package, and it is a generic function to compute what? Histogram of given variables. So I'm just going to use a few of the arguments, and the rest you can, explore it on your own at home. Now, so the first argument is x. And if you come down here, it says x is what? A vector of values for which a histogram is designed. Okay, so x will be our data set that we want to get a histogram of it. Okay, now breaks, I'll just skip it. But frequency is also important, and if you come here, it says it's a logical argument if true the histogram graphics is represented by frequencies. of the count. But if it is false, you use probability density. And remember, we have what? Frequency density, and we have what? Relative frequency density. So if relative frequency histogram. So if I want a relative frequency histogram, I'm going to say frequency is equal to false, or fric is equal to false. Okay, so that's what, and those are just the arguments that I will talk about. The rest you can, main XLab are things we have done already, and as is and so forth. You can look at it in conjunction with PAR. So for example, we can create our own as is and so forth, but those are just additions that you can always um, take it on your own. Okay, all right. So we are going to go back to the CAS 93 data set. And if you remember in our last video, we used CAS 93, but I'm going to look at the help files for CAS 93 again. And remember, there's no documentation for CAS 93. I'm committing this because people will have problems with it. And then they say, but ours says we should also try CAS 93. I hope by now most of you will know why I'm not getting help files on CAS 93, right? Okay, but I can use the double question mark or the help dot search. So let me see what happens. Okay. That's taking too long. But the main problem is that I have not uploaded my mass package, which contains the data set CAS 93. So if I want to get access to CAS 93, I must go down to my system library and then click on mass, right? Okay. And now if I can go back to my help, and then I get CAS 93, right? There it is. And now because I have mass in my library, okay. So here, because I'm interested in quantitative variable, I may use, for example, the price of the car, because it says it's mid-range price in thousands of dollars. So that's quantitative, or maybe maximum price, or even miles per gallon per city. Okay, so one way round is that we can also use the structure of the data set instead of using help, because that will help us to know what or which variables in this CAS 93 is numeric and which is not. Okay, so if you look at it from here, from the console, there are so many variables. And as I said, if we look at manufacturer is a factor, so that's not what, but of course, price, you see, minimum price is numeric, so that's something we can use. Price is also numeric. Miles per gallon per city is also numeric, and so forth. And also miles per gallon is also numeric as well. Okay, so we're just going to use price for now, and I'm going to get histogram for price. Okay, now, so first of all, we say hist. So the basic is histogram. And then I can say my X is assigned, and I get my CAS 93. And I'm interested in all price. So I'll scroll down to price, and then I plot this. So there it is. But of course, if we want a histogram, we don't want to get CAS $ price. Nobody will know what you want. And also, by default, histogram gives you the heading or the title for the figure. But as I said, this, we don't need it usually. So we will take that off. So we're going to go back to our plot, and we're going to give it more or make it more attractive. Okay. So first of all, we need to change our X lab. So our X label, we want to change it. Instead of CAS $93 price, we just need price. So we just put it here. Okay. Now Y lab is labeled correctly because that's the frequency. Unless we want to change it to, let's say, um, um, number of cars sold or what have you, then we don't then we have to change it. But other than that, we leave it as it is, like frequency. But of course, I don't need histogram of cars 93 day. So if I want to get rid of that, I'm going to say main is equal to empty set, right? I don't put any title there. So if I do this, I get my histogram like this. Okay, so basically this is how you draw a histogram. Okay, all right. Okay, now additionally, so this is basic histogram, or let me say frequency histogram. Frequency histogram, right? If I want relative frequency histogram, I'm going to copy this again because it will basically be the same. Okay, so maybe relative frequency histogram. Okay, so that, then of course I need to, by default, frequency is true. So if I say frequency is false, okay, then I do this, I get the density, right? So the graph will be the same, just that here you have what? The density, unlike the previous one. So that's what we mean. If you want to color it, you can put in color. You can color it like maybe 2, maybe 2 is red. Okay, so we color it red and so forth. So that's um, um, histogram. Okay. Now, one more thing that we can talk about. If I were to ask you to describe this, you should be in a position to describe this histogram, right? So, for example, we know that majority of the cars sold are what? Are below 20,000. Okay, so if you were to ask to make decisions, if you are, for example, going to operate a car garage, and then you are being asked, you have this data as data from sales of people or car garages, and you have this. Of course, if you want to sell your cars, faster, then you go in for cars that will be, let's say, 20,000 or less. Okay. If you go in to get cars that are over $50,000, right, then you should be prepared that in most instances you may not sell, maybe for some days or weeks or months and so forth. So these are some of the things I can ask you to do, okay, because you use your descriptive statistics to help you describe the data and also to make decisions. Okay, all right. So that's about histogram for now. Okay, all right. So that will be our discussion on histogram. Okay. So next, I move on to B, and B is stem and leaf. Okay, but before then, let me just add some few things on the histogram. So before we move on to stem and leaf, let me, for example, add, let's say, density. Oftentimes when you plot a histogram, you want to, for example, superimpose a density plot on it. You can do so in R as well. So let me add in uh, what we call frequency polygon, right? Frequency polygons, okay? Or we'll say a density curve or density curves, okay? Density curves, okay? So how do you do this? Okay, so there is a function called density. Okay. Now, so this is kernel density estimation. So if I, and that, there are several kernels you can use to draw your curve, right? And so forth. And this you will learn about some of this later on in your statistics courses. But the main thing over here is the X, which is just the data. The bandwidth, BW is the bandwidth. Okay, you can give it a number. The higher it is, the smoother the curve will be. Okay, so if I, for example, want to get a density plot of cars, the price of the cars, I'm going to plot. Okay, so you can use plot. Okay, and then you need your density, because the density will just give you computation of the density. It will not plot it. But if you want to plot it, then you must put it in a plot function. Okay, so density, I need my X is equal to what? Cars 93, the price of cars 93, right? So if I do this, this gives me a plot of my density. Okay, but I can, as I said, I can increase the bandwidth to, let's say, 2, or you can change it to see how it behaves. 1, you see. So the larger it is, the more smoother the curves becomes. Okay, all right, okay. But alternatively, if I have my histogram, I can superimpose upon it. Okay, how do you superimpose? So the plot will give you a new plot like I have. But oftentimes, maybe you have your histogram and you want to superimpose it upon it, then that's different. So plot you can, but I will come back to plot again, so I don't want to spend time on this. But for example, the main, you know that you can get it off like this, right? And then you won't have any. And even the X labs, you can name the X labs as well. So S lab is what? In this case, it is what? Price of cars. Um, yeah, you have your price of cars. So you just put price, and then that will give you um, this. Okay, so it's better than, and then the density. Okay, but what I want really is that when I have my, if I go back here, let me just delete these ones because I don't need them. Okay. Um, if I go back to my histogram, I want to be able to superimpose my density on this. Okay. So what I'm going to say is that we superimpose density plot on histogram. So there, what I'm going to do is that I'm going to use the same thing, right? Okay, but here I'm going to lines my, I'm going to use lines, right? So lines means you have a density already, okay? You have a plot already and you want to superimpose something on it, then you can do so. Okay, so this is my density plot. And if you can't see it properly, I can go back to this. You can even color your lines as well, right? Okay, so if I do this, I want to color it, I can say color is equal to 2, let's say red, okay, and there it is, okay. And of course, you can change the bandwidth if you want it to be smoother and so forth. So if I change it to, let's say 6, I'll get a smoother curve than this one. Okay, so whichever way you want to do it, you can, and so forth. So that's what we mean by superimposition of your density curve on a histogram. Okay, so That's another thing we can do. So now I can move on to my stem and leaf plot. Okay. Well, so what is a stem and leaf? Now, a stem and leaf, as you learn from your 111 plot, is that when you have a data set, you can actually split them. Let's say if they are in tens, you let the tens be your stem, and then your ones will be your your leaf. Okay. So, or if they are in thousands, maybe the thousands will be then the hundreds, thousands will be your stem, and then your below 100 will be your what? Your leaf. Now in R, um, a stem and leaf is actually not a plot because it will be shown on the console, right? So you won't see your stem and leaf on your plot area like here, but rather it will be on the console. And remember, a stem and leaf plot is just like a histogram. And the good thing about a stem and leaf is that you can retrieve the actual values back. So for example, we're going to use cars.price to do our stem and leaf. However, when we finish and you want to, for example, get the actual price, you can. However, if I had given you this histogram like I have here, you won't be able to tell me exactly what the prices of the cars were. Of course, you know the frequencies within each group, but you don't know the actual group or actual values unless I give the raw data to you. So that's the advantage of the stem and leaf over histogram. And you can turn the stem and leaf to become what? A histogram. Of course, our stem and leaf will be horizontal, but histogram can also be plotted in by using or your having your bars being horizontal. So the question, how do we go about getting our stem and leaf? In R, we use stem. Okay, so just stem like this. And you have stem, you have scale, you have width, and then and so forth. Okay. Um, yeah. And let's see. So I will just use um, the first argument, which is this. So for example, in this case, we want to get the stem of the car price. Okay, so there it is. Okay, we have it on our console. So it tells us that this is a decimal. The decimal point is 1. Okay, so the 1 digs to the right of what? The bar. So our stem 0, this means these cars were 7,000, some were 8,000, 8,000, 8,000, 8,000, 9,000, and so forth. Then you come, the first one is 10,000, 10,000. If I pick the twos, these are 12,000 because I picked the stem of 1, and then what do? I add this one. Then you get to the 20s, right? The 30s, the 40s, the 50s, and the 60s. Remember 50, we don't have anything there. But there was a car called, that was 62,000. Now, if you look at this and our plot of the histogram, they virtually um, they are all what? Positively skewed, and that's it. They are positively skewed. However, you see our histogram has more bins. But if I want to also get 1, 2, 3, 4, 5, 6, 7 bins, and when I'm plotting a histogram, I can also do so by also providing if you go to the help files for histogram, you will see your stages. Sorry. Go to your help files for breaks, I should say. So your breaks is stages, but we can actually give it a number, which is the number of um, breakpoints of the histogram. Okay, so that can also be done. Okay, so that it looks just like the stem and leaf. Okay, all right. So that's our stem, and here, of course, in a stem and leaf, we can tell which class is the modal class, of course, or here we can actually get the mode because you can actually get the actual values in this. Okay, so here, if we want the mode, um, I think that should be 16,000. Let's see. Yeah, because six. Oh, there's okay. So let me see. Count 1, 2, 3, 4, 5, 6, 7, 8, 9. What about 20,000? No, it's not up to it. So yeah. So the mode is 16,000. Okay. Yeah, but of course the modal class is between what? Um 10 to 19,000. Okay, or 19, just 19,999. Okay. All right. So that's about stem and leaf. Okay, if we want another example, we can say stem X, um, maybe cars 93. There's also miles per gallon, right? Miles per gallon highway, let's say miles per gallon highway. We can get this. Okay, so that looks also positively scaled. You can get the histogram for this, right? Okay, and yeah, maybe I can just add this just to show you what I was talking about. That if I want a histogram of this and I want breaks, I want a similar histogram for this. So I'll say breaks. How many? One, one, two, three. So seven. I want seven. Okay, seven. And then I want my X lab to be equal to um, miles per gallon of highways, miles per gallon on highway, and I don't want any main. Main is equal to dash. So let's see how my histogram will be there. Okay. So if you look at it, as I was saying, this one has 1, 2, 3, 4, 5, 6. Okay, so eventually I wanted 7, but I was given 6, right? Bars. But if you look at this and your stem and leaf, they look virtually the same, right? As in terms of the distribution and the modal class and so forth. Okay. So that's about it for um, stem and leaf, and then about histogram as well. Okay. So now the next thing I want to talk about is is box plot. Okay. Now, so what is a box plot? A box plot is one of the important basic statistical plots that can be used for quantitative data. So this, the main or the full name should be what? Box and whisker plot, right? Box and whisker plot. Okay. Now, so for a box and whisker plot, you have a box, and this box gives you the first quarter, the second quarter. Obviously the second quarter is the median, and then the third quarter. Okay. Then we extend whiskers beyond the third quarter and also below the first quarter. Now, how do you get these whiskers? Of course, you need an inner fence and then an outer fence, right? So we construct the inner fence by, subtracting 1.5 times the interquartile range from the first quarter. Then we get the inner fence for the lower part, and then we add it to the third quarter. We get the upper part of the inner fence. Of course, if you want the outer fence, you will subtract 3 times the interquartile range from K1, which is your first quarter, and then you add it to your third quarter. Now, any observation beyond your inner fence, you say it is what? A mild outlier. And if we have an observation beyond our outer fence, then we say it's an extreme outlier and so forth. So basically, that's a box and whisker plot. And any basic statistics book should have this. So if you have forgotten about this, these are things that are taught at the undergraduate level, start 111. If you have problems with it, please take any basic statistics book and look for box and whisker plot to see. But we're going to do this question. Now, to get this, to use or to get box and whisker plotting now, we use box plot. So let's look at the help files for box plot. Okay, so basically this plot needs X, but that is for a basic box plot, right? When we finish, I'm going to, when we know the basic, I'm going to add on to it that you can also use what? A formula. Why is this plot so important? It's important when we want to even compare the distribution of 2 or more groups of variables, right? So for example, we are going to use the anorexia data where we have pre-weight and post-weight, okay? I want to plot those two to check their distribution. I can do so. We're going to do several examples. And then even when we are doing an ANOVA, this is the first point of call or descriptive statistics that we can use to check whether the variations are the same or not. Of course, this is descriptive, so you can't make conclusive statement from it, but at least it gives you a pictorial view of the variation within your data and also the distribution. Okay, so the box plot. So the first thing we will do, let's look at the box plot of our the data we just used, which is the CAS 93. CAS 93. Okay. So for example, I am interested in seeing the price, a box plot of the price. So this is a box plot. Okay. Now, so what are these? So these are the whiskers. Okay. And this is the box I was talking about. So the box, this is the first quarter, right? And then you have the second quarter, which is the median, and then this is the third quarter. Now, this is the whisker. For the first one, this is what? The lower whisker, right? Okay. Now, so those values, these are values that are distinct and they are called outliers. And that's why they are in what? Those they are in points over there. Of course, your box plot, you can name the axis as well. It's just like a plot. So you can name the axis. In this case, you see you are talking about price, but it is a y-axis. So you have to say y-axis, y lab is equal to what? Maybe price of car. price of cars. Okay, something like that. And then you run, and now you have it, okay? And so forth. Of course, we can color the box. Maybe 4. I've been using numbers, so now let me probably use the names of the colors. So we know, so green, we can color it and so forth. So that's a box plot. Now, the question is, how do you interpret this? Okay. Now, look at it. If you look over here, the distance between here and the first quarter and the second quarter, right? And that one is almost the same, right? Now, if a data set is symmetric, in other words, if it's normally distributed, you expect that this box, the distance here will be the same. Also, the whiskers should be almost similar, right? In terms of the height, in this case, height of it, from the third quarter to that, and then from the first quarter to that should be the same, but they are not. So this should tell you that this data set is not what? It's not symmetric. And we've seen from the histogram that it is what? You know, if we can go back, no, this is not it. But if you scroll back, this is it. So you see, this is all positively skewed, right? This is the data for our histogram of our price. And we know that it is highly positively skewed, right? Okay, so you see, if you go back to your box plot, you can see that from it, okay? So you see majority of the data sets are here, okay? And then you have just a few over here. So if you draw your curve, it looks like that, okay? So we can also infer the distribution of a data set from a box plot. Okay, so this box plot is skewed to the right. Okay, if it was coming here, if those outliers were down there, then we would say that it is what coming from what it's left skewed and so forth. So this is a positively skewed data. Okay, so that's how we construct a box plot. Maybe we should get another one as another example. So this one is a box plot for price of car. Now, I want to use another data. So, or let me use the same data. And then we did talk about miles per gallon for highway, right? So for highway. So let's now see how that can be done. Okay, of course, I need my cars 93 miles per gallon. Okay, now I'm going to use city. Okay, so instead of highway, I'm going to do city. Okay, and so I change my Y lab to be what? MPG for city drive, for city, something like that. And my color, maybe now I want yellow. Yellow, okay. So I can do this. And there it is. So that's also positively skewed, right? Okay, all right. So that's another example. But now I want to do the case where I have two or more variables. Okay. Now, so here I'm going to talk about the anorexia data. I'm going to use the anorexia data, right? So remember that the anorexia data we had what? Pre-weight and post-weight. Let's just look at it. Let's just look ahead. So we want to see just a few. Okay, so there it is. Okay, so here I want to check whether pre-weight and post-weight, how they compare. Okay, all right. I can do so quite easily by also passing this to box plot. But remember, treat is what? Is a factor. And this box plot is for what? Numeric data, right? So if it is for numeric, I am not interested in what? Treat. So the box plot show few observations. Show few observations of the data. Okay, now I want to plot. So I want to get a side-by-side box plot, if I should put it that way. That will show me pre-weight and post-weight, right? So what do? I'll say box plot, and please note, I don't want I'll pass in an erasure, but I'm going to take out the first column because I don't need the first column because it is treatment, which is categorical data. So I don't need it. So this is what I'm going to do there. So you see, you can pass in as an argument a matrix, and what box plot does is that it will plot each each column because the columns are the variables. So that's what box plot will do for you. And here we can go back and maybe rename it if we want to. So X lab should be what? Should be, sorry, we mean the Y lab should be weight of female. Okay. And then we can plot again so that we know our, oh, sorry. No, we need this to be Y rather. To be Y. And our X lab, if we want to name it, should be so this is the weight before and then after. So what should I put there? Maybe the weighing time, right? Weighing time, for example. And then I can plot this and we get something nice. Okay. Here I can also plot, I can color them if I want by using two colors, right? So maybe 2 to 3, right? And then each of them will be given red and, you see, so red and green and so forth. So there's so much you can do, you just explore what else you can do. But now I want us to interpret these two box plots. Okay. So first of all, if I look at this, can I say that it is symmetric? Well, it's not so far from symmetry, but it is a bit skewed. Look at the distance from the median to the third quarter. It is longer than from the median to what? The first quarter. Okay. But if you look at the whiskers, they are almost the same. So this is not far from normality. Okay. Now, if I look at the post-weight data, you see this whisker is shorter than that. Of course, the distance from here to there is also longer than that one. So that is far from normality than this one. But here, your interest is to compare whether the females are actually gaining weight. So what can you do? Well, if you look at here, we can say that generally the post weights they weigh more than what? The pre-weight. Okay, so we can say that people actually got what? Yeah, I mean, got some increase in weight because look at it, the whisker over here is larger than that one in terms of size or weight, I should say. Okay, now However, if you look at the first quarter over here, the first quarter is higher than the first quarter for the post weight. The median for the post weight is larger than this one, and of course the third quarter is also larger. This one is also larger than that. Okay, so yes, there is some general increase in weight, but we cannot stick our head out now because this is descriptive statistics. We'll come back to this when we talk about t-test, or so that we can compare these two populations to see whether there exists a significant difference between the average over here and the average over there. And I'm using average instead of mean because if we are using mean, then it means they should satisfy normality, and also it should satisfy normality. Okay, so and the check, we also check about variances, whether the variances are the same, and so forth. Yeah, okay. So but we can test concerning the means as well. So that's it. And this is more variable because you have in terms of the spread, it's larger than this one. So that's how the information you cannot glean from what a box plot, especially when it is comparing two things. Okay, so that's about it for when you have more than two. But more importantly, you can also input in the formula. Okay, so I'm going to use the same anorexia data. Remember, you see the anorexia data, if we display all of it, you have what? You have several, the treatments are 3, and then post-weight. So I may be interested in getting, let's say, box plot for only those who got treatment or were in the control group. And then also I want to get a separate box plot for those who are in the CBT group and those who are in the family treatment group. What is the essence of this? This will help us to compare the weights of the people from the control through CBT to FT. Now, how do you go about this? Okay. Now, for this part, so here I'll say when you have a side-by-side box plot, side-by-side box plot. Okay. Now here, I want to get input in a formula, or I want to do this plot such that I have 3 plots, each of them relating to the treatment. Okay, so how do I go about this? I want to take the post weight, and when I finish, place as an exercise. You can also do that for the pre weight. Okay, so what I will do is that I'll input in a formula. So I'll first call for the data, and my data is anorexia. So I'll just copy anorexia and paste over here, right? Okay. Okay. Then from this data, I want to use this. So I'll just copy this and, sorry, I want post weight. So let me just copy post weight. I'm copying so that I don't make a mistake of this. So I want to plot my post weight on treatment. What it means is that this tells Boxplot that please do Boxplot, but do plot my post weight based on the treatment the person received. So let's look at it. You see, I have 3 different treatments. Okay, so I can even add more of it. So I can add more arguments. My S lab, that is the treatment type. Treatment. What about my Y label? My Y label is post weight. Post weight. I may want to color And then color, because control is just a placebo or control group, maybe I may be interested in leaving it blank. Um, so I'm going to say red, white, and then maybe blue. Okay, so there we have it. Okay, so the control is this. Now the question is, can I say that, or I should ask you, which of these treatment is good or better? Now, if I ask you this question, what are you going to do? Well, look at it. You see, the control group, what is the aim of this experiment? You want people to do what? To gain weight. Of course, so the treatment that will give you more weight is supposedly be the best. Okay. So first of all, if you look at family treatment, it seems to have majority of the data set way above the other two. However, look at these three. These are outliers. So there were about 3 people, or either 3 or 4 people, that had very low, weight compared with all this. Okay. Now, from family treatment, the next one is what? CBT. So CBT is largely better than the control. But remember that they are overlap. They overlap. Okay. So all of them are overlapping. So when we want to check this, to be able to stick our head out, we must conduct a hypothesis test. And a hypothesis test to compare 3 populations here will be an ANOVA, if all its assumptions are satisfied. But here we can say, or this one I can say categorically, although I have not conducted a test, that for the family treatment, it doesn't follow normality, right? Because there are extreme cases within it. But the CBT is quite normal. Control is, I can say, close to normality, but the CBT is not. Okay. So that's how you can um, do this, right? And talk about some of these things. So please, for your exercise, do this plot or repeat this. Repeat this for the pre-weight group. Okay. So please do that. Okay. I want to do a last one. There's another data set called insect sprays. Now, if you look at the helpers, that is also in data sets. Now, so insect sprays, you can read about it, but essentially it's just some sprays that were used in an experiment, right? And then they spray it, and then you go and check which and count the number of insects that are remaining. Okay, so if you want to see what this, it says it's made up of what? 72 observations on 2 variables. So count and so forth. So if you look at this, you see this is how it is. So spray A, B, C, D, and then the count. Now, one will be interested in knowing whether the sprays are significantly different. In other words, the rate at which they kill insects are significantly different. One easy graph you can use to compare this is the box plot. So just like I have done, I can also plot these insect sprays. Okay, so box plot, of course, first of all, I do my data. My data is insect sprays. insert sprays, and then I can come here and copy the headings. So here I'm going to plot count against what? On sprays. So count. And please, if you are not seeing this, this is tilde. Usually it is located at the top left corner of your laptop, right? Just below the escape. But of course, I am using HP. I don't know what you are using. If you are using Mac, it may be different. Like Apple and the others, I'm not so sure. So please check. That is the tilde for the formula. Okay, so I can do this. Okay, so that's it. These are the insert sprays. If I want to color them, I can color. Okay, and this one, maybe we can use the rainbow 6 as well. There are 6 groups, right? So 6. Okay, so 6 groups. And maybe I can go back again and do the Y lab. I can say count of inserts just so that it gives proper labeling. Okay, and then X lab is spray. Okay, and so forth. So that's it. So if you look at this, okay, so I'll leave this to you as as part of your, because I have explained some of this in the previous ones we did. So please, I want you to talk about, or just write some short notes on the graph you see over here. Will you say they are the same? And please read, as part of your assignment, please read, get so that this source or the journal, and please read just the preamble, the abstract. You will be able now to interpret the graph in relation to the experiment they did. So by the end of this assignment, you will be in a position to get what? To be able to get a journal paper online. You see, you can have access to this either through Google. If it's not working, you can also go to BAM library, access your login through your off-campus login, and then you'll be able to get through the biometrical journal and be able to download this paper. Read it, and then you will be able to know what these count of insects are. And after that, you will be in a position to tell me which of these insect sprays you will recommend for, let's say, farmers. Is that okay? Please, so that you will know whether this the lower count is better or upper count is better. But through this, you are doing an exercise where you get a journal and you'll be able to read to know what it is talking about. And then you'll be able to interpret the graph that you have done in relation to the data. Okay, so that's it. And that ends my discussion on Boxplot. Okay. Now, the next thing I will talk about is